Okay, we're going to continue on now with the topics in Unit 2. So last session, we talked about electrostatics and how objects become charged. And the key thing to remember is that objects become charged by either gaining or losing electrons. If they gain electrons, they become negatively charged. If they lose electrons, they become positively charged. It's never because protons move, because protons are locked inside the nucleus. They do not move. Remember that. Very important. All right, so let's continue on now and talk about something called Coulomb's law. And Coulomb's law tells us, we already know that opposite charges attract each other and like charges repel each other. So if there's an attraction or a repulsion, then obviously there's a force there. Well, Coulomb's law allows us to determine the size of that force. So that's what we're going to talk about in this recording. So we've already talked about opposites attracting and like charges repelling. So it'd be very, very handy if we could actually figure out how much they repel or how much they attract. In other words, how much force there is. So in order to do that, what we're going to do is we're going to consider point charges. In other words, all of the charge would be concentrated at a single point. And it's very similar to what we talked about when we did the section in static equilibrium. We talked about all the mass of the object being considered to act at the center of mass. So it's a very similar idea to that. It doesn't necessarily have to be that way, but for purposes of calculations, we consider that to be the case. So electric charge obviously is going to depend on how many excess or deficit electrons we have, because an electron is what we call the fundamental or elemental charge. Okay, the fundamental charge. In other words, we can't have a unit of charge smaller than one electron, because that's what causes charge in the first place. So every time we have an electric charge, it's always going to be a multiple of the charge on an electron. So essentially what we're going to say is that Q equals NE. Q represents charge. That's the symbol we use for electric charge. The letter N represents the number of electrons, and the letter E represents the electron charge. And the electron charge is actually negative 1.6 times 10 to the negative 19 coulombs. Now on your data sheet that you get with your public exam, it's going to say that E equals 1.60 times 10 to the negative 19. That's 3 significant digits, but using 1.6 is going to give you the same answer. You just have to be careful with sig figs, that's all. Electric charge is measured in a unit called a Coulomb. A Coulomb, C-O-U-L-O-M-B-S, coulombs. And it's named after the gentleman who discovered it and who did a lot of early work in the field of electrostatics and came up with a relationship between the size of the charges and the distance between them and the force of attraction or repulsion. So that relationship became known as Coulomb's law for obvious reasons. Okay, so what Coulomb discovered was that the size of that force depended on really 2 things. Number one, it depended on the size of the charges. In other words, the bigger the charges, the bigger the force. That makes sense when you think about it. But it also depends on the distance between the charges. Now, if you think back to Physics 2204, you may see some similarities there with the law of universal gravitation, because there's a very similar relationship. In fact, the formula for Coulomb's law is almost identical to Newton's law of universal gravitation. The only thing is we have a different constant in there, and we use charges instead of masses. So what we're going to do now is we're going to take a look at how that law actually works. Okay, so Coulomb's law is a way of determining what the force is. Okay, what the force is between 2 charged objects. So remember, it depends on 2 things: the size of the charges, in other words the Q's, and the distance between them. So the electrostatic force, it turns out, and this was discovered by Coulomb after he did some work in this field, but he discovered that, typo there, sorry about that. He discovered that the charges were what determined it. Okay, the charges on the two objects. I was getting caught up in the analogy there with Newton's law of universal gravitation. But it's obviously the electrostatic force, the force, in other words, between two charged objects, depends on the charge on each of those objects, the Q. So that's why the letter Q is there. So we say QA, QB, we can say Q1 and Q2, it really doesn't matter. But the point is the electrostatic force is directly proportional to the size of those charges. So if we doubled one of those charges, we'd double the size of the force. If we doubled the other charge and left the first one constant, we'd still double the size of the force. If you doubled both charges at the same time, you'd have 2 times 2, or 4 times the force. Okay, that's how Coulomb's law works. So that's the relationship with the charge. There's also a relationship with distance. And similar to the way that the law of gravitation works, it's an inverse square relationship. In other words, it's inversely proportional to the square of the distance between. And we always measure distance between the 2 point charges, between the points where the charge is said to be concentrated. Okay? So 1 over r squared. So putting it all together, we get this proportion. And we call it a proportion because there's no equal sign there, you'll notice. We use that proportionality symbol, the one that kind of looks like a fish, the Greek letter alpha. So it's QA times QB over r squared is proportional to the force. And what we're going to do now is we're actually going to look at some examples of how that applies to problems that you might see on the public exam. Because every now and then, instead of asking you what the actual force is, they might ask you what would happen if you did this, or if you did that. Okay, so those are the kinds of things that we're going to look at here now. We're going to look at some multiple choice questions. So first of all, we'll look at one that deals with charge. Okay, and that's the one that uses this relationship. Remember, we said a minute ago that Q equals N times E. In other words, the charge on an object depends on the number of either excess or deficit electrons. So for this one, the charge is negative 0.150. So negative 0.150 is equal to N, we don't know, but E is negative 1.60, and this is straight off the data sheet, times 10 to the negative 19. That's the charge on one electron, and one only. So if I divide both sides by 1.60 times 10 to the negative 19, I'll end up with N equals 9.38 times 10 to the power of 17. That's how many excess electrons are on that metal sphere. That's what would cause that amount of charge. Now that's a lot of electrons. That's millions and millions and millions of electrons. And that's not even a full Coulomb of charge. 1 Coulomb of charge is an extremely big amount of charge. It's not unusual to have charges like in the order of 10 to the negative 5 and 10 to the negative 6. Okay, that's fairly common. In fact, charge is often expressed in microcoulombs. And 1 microcoulomb is equal to 10 to the negative 6 coulombs. In other words, a microcoulomb is 1/millionth of a coulomb. That's a pretty typical charge. So you might wonder, why is a coulomb so big? Well, it's just the way it got worked out to be, that's all. No particular reason for it. So there is how you use that formula, Q equals NE. And you do use that occasionally. It's not on the public all the time, But there's often something there that you have to use that relationship for, so it's nice to know it. Now, look at the second one. The electrostatic force between two charged spheres, X and Y, doubles. So remember now, we said that the electrostatic force, Fe, is proportional to Qa times Qb over r squared. Now, if the force between them doubles, what could account for that? What could explain that? Well, let's just look at them one at a time. Let's look at A. If the charge on sphere Y doubled, would that make the force double? And the answer is yes, it would. If the charge on one of them doubled, because force is directly proportional to the size of the charges, then if we double just one of the spheres, that would double the force. So A is the right answer. That's the best one. And by the way, C was the right answer up here. So that is the right answer. That is the right answer. Part B said, or B of that one said, the charge on one sphere, only sphere Y, was halved. But if you only halved the charge, that would halve the force. Because remember, directly proportional. Whatever happens to one, exactly the same proportion will occur with the other. So if we half one, we half the other. If we double one, we double the other. It's as simple as that. The distance, remember, is an inverse squared relationship. So if you doubled the distance, okay, like I said, this one here, that would half the force. If you doubled the distance, that would be 2 squared, which is 4. But because it's an inverse proportion, it would be 1 over 4 times F. It would be only a quarter of the force. And the last one, if you halved the distance, a half squared is 1/4, but because it's an inverse proportion, it would be 4 times then. 4 times F. Remember, the closer together they get, the stronger the force of attraction or repulsion gets. That's the way it works. All right, let's look at the last question there. The electric force between two charges is 0.012. We want to know what would be the new electric force if the distance between the charges is doubled and the value of one charge is tripled. So the way I usually tell my students to do these is I usually say, remember that F is proportional to Qa Qb over r squared. And let's look at what's happened here. The distance is doubled. So I've got r times 2. One of the charges is tripled, so I'm going to say Qa times 3. And the other one, it doesn't say anything happened to it. So if nothing happened to it, we just say 1. So here's what I'm going to do. I'm going to say Qa is 3 times bigger. Qb is only 1 times bigger. It doesn't change, in other words. Divided by r squared means 2 squared. So I got 3 times 1, which is 3, over 2 squared, which is 4. What that tells me is I've got 3/4 times my original force. My original electric force is going to be 3/4 of what it used to be. Well, it tells us what it used to be. It tells us that the force was originally 0.012. If I multiply that by 3/4, I get 0.009, which obviously is choice B. Okay, choice B is the right answer. Because both of those things affect the force. So both of them happening at the same time have a combined effect. Now what you could do is do it this way. You could say the distance between the charges doubled. That means it's 1/4 of the original value. So you could say the 0.012 divided by 4. And then you could say that number then changes again because the value of the charge is tripled. So that means 3 times that force. Then you just multiply that by 3. And you'd still get 0.009. Same answer. just a slightly different way to do it. But this is a pretty systematic way to do that. That'll work every time. Okay? And it's pretty easy to follow. It's almost like using an equation then, because a lot of people have trouble with the proportions trying to work them out in their heads. So that's a nice way to do it. It's an easy way to follow. It'll always give you the right answer as long as you don't make any mathematical errors. But it's pretty good. It's pretty easy. Let's try a couple more. This time it says we've got two charged particles separated by a distance d. Separated by a distance d. So it says, what happens to the magnitude of the force between the particles if the distance is divided in two? In other words, if we halve the distance. Well, remember, F is proportional to QA over times QB over R squared. Notice there's no equal sign here. So the two charges don't change. So I got 1 times 1 over, I got half the distance. So it's a half squared. 1 times 1 is 1. A half squared is 1 over 4. So really what I've got is 1 over 4. In other words, the reciprocal of 1 over 4. So 1 over 1 over 4, or 1 divided by a quarter, is 4. That means 4 times my original force. So therefore, it would increase by a factor of 4. Increases by a factor of 4. That's it. Done. Okay, it really is that simple. Let's take a look at the last one. Same type of idea. Again, force proportional to charge A, charge B. Now, if you're used to saying charge 1 and charge 2, that's fine too. I don't care. It really doesn't matter which way you write it. On the formula sheet, it's actually written as Q1, Q2. I'm just used to writing it as QA, QB, so there you have it. Again, this time it says one sphere is doubled. So I'm going to say 2, nothing happens with the other one. So 2 times 1. That's my two charges. One is doubled, the other stays the same. The distance is also doubled. So on the bottom I've got doubled means times 2 squared. So what I've got is 2 times 1, which is 2, over 2 squared, which is 4. So I've got a half times F. In other words, my force is cut in half. So which one of those matches that? Well, a half of F means, first of all, it gets smaller, so it decreases. And if it's a half, it decreases by a factor of 2. So the answer is A. Those proportional problems are usually on the public exam. There's usually one there like that. Not all the time, but you can see we had 3 or 4 different ones here. I only looked at 6 different exams when I was taking these questions. I took these questions off 6 different exams. 4 of those 6 had a problem like this. So it's a pretty safe bet. That's about 2/3 of the time you'll see a question like that. So will you see one this year? Who knows? Maybe you will, maybe you won't. But because it's such it's such a high percentage of the time it's there, it's always good to be prepared for that. But it's not hard to do when you do it like that. And if you find it hard dealing with proportions, then by all means, stick some numbers in. Make some numbers up and put them in and see what happens to the force when you make the changes. Then you can just take the two forces and divide them, see what you get. That'll always work. So that concludes the second topic in Unit 2, Coulomb's law and proportions. In the next topic, we're going to take a look at Coulomb's law again, but we're going to look at the equation for Coulomb's law this time. And we're going to look at some problems where we look at a combination of forces, and we have to add the forces together, usually as vectors. So that's where we'll pick up in topic 3. So again, good luck in your studies. Work hard, and you'll find the exam just fine.